Okay. All right, recording, perfect. Okay, so let's get started. What chapter do you want to start on? Chapter 7, 8, 9? 7. Okay, so we'll just go in order, perfect. Okay, so hopefully because there's very little calculations in this midterm, hopefully it's gonna go by fast since there's no calculations. Okay, so let's start with chapter 7. I like how all the concepts in this, this sequence of chapters, they really go along with one another. So in chapter 7, we're looking at properties of elements, of atoms, and we can use those properties to predict the bonding nature in chapters 8 and 9. The reason why ionic compounds are formed from metals and nonmetals has to do with ionization energy, electron affinity, and lattice energy that comes out. And then we look at, more details in covalent bonding. So let's look at chapter 7. We're expanding on the idea of electron configurations. So here, let's get the electron configuration for the following things. Notice that they're not elements, they're ions. So what we want to do is start with the neutral element. So of all things to have today, it's the periodic table. So let's write that electron configuration for the neutral element first. So for nitrogen, we have a noble gas. So these are skills from chapter, or from midterm 3 that we just had. So we have a helium noble gas. We move on to row 2. So this is 2s, fill up 2 electrons, and then 2p, fill up 3 electrons. That is a neutral nitrogen atom, but we want to look at the anion. So that means since we're making a 3- anion, we have to add 3 extra electrons. What is the most likely place those electrons will go? Are they going to fill up in the 2s? No, because that's already filled. They're going to most likely occupy that 2p. So if we add 3 electrons, our new electron configuration will be that noble gas, 2s2, 2p6, and this is actually equal to a neon noble gas configuration. And that's why typically when we find nitrogen as an anion, we'll find it with our 3- charge. So remember in chapter 2 when we just had you memorize, hey, all group 7a elements adopt a -1 charge. All 6a elements adopt a -2 charge. So the reason we had you memorize that is because that relates and agrees with this idea of adding electrons to fulfill these noble gas configurations. They're octets. But it has to also do with energetics, which we'll talk about later. All right, same thing for magnesium. So always start with the noble or the neutral element first, and then just add or subtract electrons as necessary. So magnesium is neon 3s2. So if we're making a 2+ cation, we're going to remove 2 electrons. There's really only 2 electrons to remove. So magnesium 2+ electron configuration will simply just be a neon shell. All right, we're removing the highest energy electrons. So these last 2 examples are a little bit trickier. Right, we have a tin example. So tin, let's do the same thing, write out its full electron configuration. So we have a noble gas, in this case it's what is that, krypton. So krypton goes to rubidium, so that's 1, 2, 3, 4, 5. So this is 5s2. Then 4d10, we're gonna fill all of that up, and then 5p2, right? So that is their neutral tin atom. In this example, we want to remove 2 electrons, but we need to be careful, all right? So especially when D block elements, I'll actually add one more example here, but we need to be careful here because there's lots of different subshells that we can remove from, but in general, we always want to remove from the highest energy subshell possible. So that means we want to either remove 5s electrons or 5p electrons. We're not going to remove both of them because in this example, we want a tin 2+ cation. So we have a choice. Do we want to remove the 5s electrons or the 5p electrons? In this case, we actually want to remove those 5p electrons. They are the highest energy electrons. They're at the top of the barrel in this example. So tin 2+ is simply going to be that noble gas, 5s2, 4d10. right? And so if we want the 4 plus cation, if we start at the neutral element, we want to remove 4 electrons. So in that case, we will remove both the 5s electrons and the 5p electrons. So this one, what's going to be left are just those 4d electrons. Right? So in this case, we are always removing the highest energy electrons first, especially when the d elements or the d block is starting to be added, especially if you have a full d block. Those electrons are really low in energy, that it takes a lot of energy to remove them. So typically, those don't get removed from our electron count. We remove higher energy electrons first. Let me give one more example. Let's do zinc 2 plus. What do we think the electron configuration of zinc 2 plus will be? So let's start with that neutral element. So we have argon 4s2 3d10. All right. So in this example, we need to remove 2 electrons to make that cation. We have 2 choices of subshells to remove from. And so here's the trick. With transition metals, you always want to remove your highest energy electrons first. They're typically in the s subshell. We're going to remove these n equals 4 electrons before we remove the n equals 3 electrons. That can be quite, I guess, confusing for a lot of students, because when we think about writing out this electron configuration for zinc, we placed the 3d electrons first. So you would think, oh, if we want to remove electrons, we just reverse the order. But we don't do that. So for transition metals, listen to me closely, the order you place the electrons is not the order you remove them. Right? Nod if you're catching along. So here in zinc, we placed the electrons in the 3d subshell last, but in this example, to make the cation, we're actually going to remove those 4s electrons instead. So the 2 electrons we remove are going to be those 3s. So our electron configuration will look like this. Noble gas 3d10. Notice how this is kind of analogous to our tin 4 plus example too. Notice that we're never touching those d electrons. All right? Got it? Okay. All right. Okay, so that is electron configurations of ions. Just do think about those little tricks, especially with transition metals. So the other thing we learned about in chapter 7 was this new idea, effective nuclear charge. Effective nuclear charge is a concept that's super, super important because it explains a lot of weird properties we see about the periodic table, particularly size, and it'll help us understand why we see certain trends in ionization energy or electron affinity. The better you understand effective nuclear charge and what that means about that electron, the better off you'll be in this chapter. So what is effective nuclear charge? I use an analogy, a Taylor Swift analogy, but let me just kind of start this question. So let's compare the effective nuclear charge, that's what Z effective is, of a sulfur atom. So what I usually do is write out the full electron configuration for that element. So if we're looking at a sulfur atom, and I'm gonna just write the full electron configuration, 1s2, 2s2, 2p6, what comes next? 3s2, 3p4. Right? So looking at this full electron configuration, how many energy levels have we filled? We have n equals 1, we have n equals 2, and we also have n equals 3. So when we think about this atom, we have like our positively charged nucleus. We have a n equals 1, we have a n equals 2, and we have electrons in n equals 3. So I like to think of this like a concert, like a Taylor Swift concert, all right? Where Taylor, she's the nucleus, she's where all the protons are. So what is the charge on sulfur? Positive 16, right? So if you're an electron sitting in the first row and you look into the nucleus, if you look into the stage, what charge do you see if you're this electron sitting in the first row at that concert? You see the full positive 16, right? So you're like really attracted to that, right? Since you're a electron and you're negatively charged, are you attracted to a plus 16? Heck yeah, because it's positive and negative. Okay, so now let's go to a different spot. Let's go to a different seat at this concert. Let's go to n equals 2, all right? Let's be an n equals 2 electron, all right? So now you're sitting in the second row. You're an electron sitting in the second row, but remember, there are electrons sitting in front of you, okay? But can you tell me how many electrons are sitting in front of you? So if we're sitting here in the second row, look into the nucleus. How many electrons are sitting in that first row? It's right here in the electron configuration. How many electrons are in that first row? 2. So there are 2 electrons right here, and they are shielding you from Taylor-Swift's radiance, all right? Because we're all negatively charged. Here's an electron, and you're an electron. So if you're sitting in that second row, there's my eyeball, you look into the stadium, into the stage, do you see the full positive 16? No, you're shielded by 2 electrons that are negative 2 overall. So what net charge do you see? Positive 14 instead. And so what we essentially just did was kind of calculate the effective nuclear charge of this 2s electron. The effective nuclear charge of that n equals 2 electron, it can be a 2s or a 2p electron, is equal to the full charge of the nucleus, so positive 16, minus the number of electrons that shield it, which the definition of shielding, it's the electrons that are just in lower energy levels. So we're just counting the electrons that are between the row that you're sitting in and the nucleus. So in this example, it's minus 2, right? So in this example, it's 16 minus 2, so this would be what, plus 14 that we got, right? So your front row electrons, they feel the full plus 16. These second row electrons only feel a positive 14, right? So then let's do the same thing for these n equals 3 electrons, all right? So what if we're in the third row? We're in the third row, right? So if we're in the third row, I'll do a different color here. Our effective nuclear charge is still going to be plus 16, but we want to subtract the number of electrons that are shielding us. So just look, how many electrons are sitting in rows between you and the nucleus? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Do you agree? Yes, so the Z effective for these n equals 3 electrons is positive 6, all right? So based upon that, what electrons are more attracted to the nucleus? These n equals 3 electrons, so plus 6, or these n equals 1 electrons? They experience a what effective nuclear charge? Plus 16. So which electrons are more attracted to the nucleus? These n equals 1 electrons, those electrons in the first row of the concert are much more attracted to the nucleus than those outer valence electrons. That makes sense because those electrons, they sit closer to the nucleus. The more attracted an electron is to the nucleus, the effective nuclear charge, typically the smaller the particle. And that's how we calculate effective nuclear charge. Just to continue the Taylor-Swift analogy with the shielding calculation, we're only ever calculating electrons in lower energy levels than us. So you're only counting the electrons that shield you are only the electrons between you and the stage. So a lot of students, they'll ask me, because like a question could be like, what is the effective nuclear charge of these 3p electrons, right? It's still going to be positive 6. But a lot of students will be like, well, when I look into the stage, don't the 3s electrons, the 2p and the 1s electrons shield me? So in this case, when you're in a 3p subshell, these 3p electrons, they're in the same row as those 3s electrons. So the analogy is all of these n equals 3 electrons, they're all sitting in the same row at the concert. So when you're at this concert, who is really affecting your like full concert going experience? Is it the people standing in front of you or the people sitting next to you? right? The people sitting next to you, they're in the same row as you. So they're not affecting your, full view of Taylor Swift on the stage. It's only the people that are sitting between you and the stage. Does that make sense? Right? So if you're calculating the effective nuclear charge for either these 3s or these 3p electrons, they experience the same effective nuclear charge. Same thing with these 2s and these 2p electrons. They experience the same effective nuclear charge because they're all in the same row. So do keep that in mind. All right? So, okay, so I guess we did that. I guess to truly answer the question, for sulfur, your valence electron experiences a positive 6. Your 2s electrons experience a positive, what did we get, 14. And just for completeness, a 1s electron experiences a positive 16. All right? So then answering these questions, what electron experiences the larger Z effective, which electron is more attracted to the nucleus? It's going to be those 2s electrons. Because if you were just a dumb little electron that's negatively charged and you have a choice to go from, to be attracted to a plus 14 or a plus 16, I'm going to choose that plus 14 because it's a higher positive number, and as a negatively charged electron, I am more attracted to that higher positive number. All right, and then, yeah, same idea here. That 2s electron is more attracted to the nucleus because it experiences a higher Z effective. The electron is more attracted to it, right? So higher attraction, higher Z effective, closer to that nucleus. And we're going to use that to predict a lot of sizes coming up here, all right? So there's a trick for effective nuclear charge, all right? Because, we don't want you to be doing this Z effective calculation all the time, right? Z effective is the equation we give you is Z minus S, right? You technically don't have to do this all the time because there's a trick, especially with valence electrons, all right? So the trick is for valence electrons, any element, its Z effective for valence electrons is also equal to the group number of that element. Let's just check and see if that holds true. What did we calculate sulfur's Z effective for its valence electrons was? What did we calculate that? Plus 6. What group is sulfur in? Plus 6, all right? Let's just do another one real quick. Let's do lithium. Let's do like a really quick one, lithium. What is the effective nuclear charge of a valence electron on lithium? Let's write out its electron configuration, 1s2, 2s1. Our lithium nucleus is positive 3. So if we're a valence electron, we're sitting in this second row. All right, so sit in that second row, look into the nucleus. How many electrons are shielding us? 2. So that means Z effective for this 2s electron is 3 minus 2, so it is plus 1. So those valence electrons on lithium experience a plus 1. What is the group of lithium? Group 1, all right? So that is the trick. It only works for valence electrons. So let's just try this out. What is the effective nuclear charge of a valence electron on carbon? Just yell it out. Positive 4. I like to say positive 4. Why? Because I want to remind myself that it's a positive charge attraction to the nucleus that electron's going to feel. All right, what about chlorine? Z effective. Plus 7. Okay, what about aluminum? Plus 3, all right? Okay, so perfect. So it's just group number, that's for valence electrons. And we're going to use that in question 3 where we are predicting size, all right? We want to know which of these pairs are the larger thing, right? This is the strategy. You always look at N value first, right? Look at your elements involved. If they're in different N values, just go off N value. So for example, if I had lithium and sodium, comparing those, sodium is going to be bigger because it's an N equals 3 element. Lithium is an N equals 2 element. Sodium literally has way more electrons, way more shells. So it's going to be the bigger atom. So always look at N first. If you have 2 elements in the same N, you're going to look at Z effective. right? You're gonna look at Z effective, where things that have high Z effectives are typically smaller atoms. And so what that means, these two things together, the general trend on the periodic table, what we see is that size increases going down the periodic table, but going left to right, how does Z effective change left to right across the periodic table? It increases, so that means size decreases, and that's really weird. All right, it's weird because when we go left to right across the periodic table, we're going up in mass, right? The things are getting heavier, heavier, and heavier. Typically, when we think things get heavier and heavier and heavier, they get bigger and bigger and bigger, but that's not the case within a period. That within a period, our elements actually get smaller and smaller and smaller because the effective is increasing until we open up a new shell. All right, so that's the strategy there. Also, we're gonna look at ions. Sometimes cations are always smaller than their neutral element. The reason is because to make a cation, what do you do with the electrons? You remove them. So they're always gonna be smaller because there's literally less electrons there. Anions on the other case, if you were comparing, I think this example, this first one, F minus or F, which one of these is larger? F minus, the anion, because there's literally more electrons there. And then there's some weird examples, an isoelectronic series, so things with same number of electrons. We'll look at that in the last example. So let's go through all of these. So A, that example, it's fluorine anion or regular fluorine. F minus is the larger thing because there's literally more electrons present there. All right, so here electron repulsion is the reason why F minus is larger. All right, next, N and P. So locate those on the periodic table. Actually, do I have a periodic table that I can copy? Man, I'm really bad. Let me just go somewhere real quick and grab a periodic table. All right, so I'm gonna just grab this periodic table and keep it handy with me. In this packet, okay. Okay. All right, so then I can circle, all right, we're gonna compare nitrogen and phosphorus. So what is the criteria that differentiates these things? N, Z effective, what are we looking at? N, and so what's the bigger one? Phosphorus, again, because of N. All right, germanium and selenium. So let's locate those. It is, where is that? GE is right there, SE is right there. So notice that these two elements are in the same N. So can we differentiate on N? No, we're looking at Z effective in this case. All right, so I like to think of it this way. Germanium, its Z effective is plus what? What group is it in? 4. Selenium is what? Plus 6. If you're a dumb little negatively charged electron, you are more attracted to which one of these things? Plus 6. So that means selenium is going to be what? Big or small? Small. It's going to be small. So the bigger thing in this case is germanium. And the reason is Z effective. Right, and so that follows this, periodic table guide here, going left to right, size decreases, right? Okay, last one, and this is a weird one, so we kind of have one of each example. We have I minus and cesium. So at first glance, when I circle these things, we have, what is this, cesium right there, I minus right there. So at first glance, you might be like, oh, they're in different N values. But notice that these examples are cations and anions. So cesium in this example doesn't have 55 electrons. If it's cesium plus, there's actually only 54 electrons present. If we are looking at I minus, normal iodine has 53 electrons, but I minus has 54 electrons. So this last example is a special case where both particles have the same number of electrons. So how we differentiate the size is we look, hey, they're different elements. These elements have different number of protons. Iodine has 53 protons, and cesium has 55 protons. So let's look at these two examples. Both of them have this cloud of 54 electrons circling it, but one of them is circling a positive 53 nucleus. The other one is circling a positive 55 nucleus. So which one will be bigger just based upon attractions? The I minus, all right? Because there are less electrons there, or sorry, less protons. A not as positive charge for those electrons to be attracted to. So it's all about attractions. High positive charges means that your electrons are highly attracted to that thing. All right, good? Okay, all right. Let me do one more example. What about Br minus and I minus? Which one's gonna be the bigger one? All right, so notice that they're both anions, so that we're gonna add one electron to each of their counts. But notice when we do that, right, bromine's right here, iodine's right here, we're just gonna add one electron to both of those. So iodine's gonna be the larger thing here because it's in a different N value. It's in a way different N value of bromine, all right? Even though they're both anions, I can still tell one is a lot larger because of the N value. All right. Okay, so with that in mind, if we know size, then ionization energy is a lot easier for us, all right? So ionization energy trends, for the most part, with size. The definition of ionization energy is energy to remove an electron. So I like to think of it like this. If you were trying to steal something from me, like an electron, would it be, if I was holding the thing, if you wanted to steal an electron from me and I was holding it really close to myself, then would it be easy or hard to take it from me? Really hard, yeah. But what if my electron was sitting over there, like in the other room? Would it be easy or hard to take that electron from me? Really easy. So what we see here is that energy to remove an electron is inverse with size. Small things have really high ionization energies, right? Large, big, fluffy things have really low ionization energies, meaning it's very easy to take an electron off of it, right? So for like 95% of the time, ionization energy trends with size. So let's look at some of these. K and Ca. So let's bring our periodic table down here. All right. So let's highlight where those are. We have K and Ca. So notice they're in the same row, but they have different effective nuclear charges. So which one is it harder to remove an electron? It's going to be the smaller thing. So which one's smaller, K or Ca? Ca, all right? So in this case, Ca has the larger ionization energy. It's harder to remove that electron. The reason is because Ca is smaller. It is smaller because of Z effective, all right? Next one, K or Rb. So here's K, here's Rb. So which one is it harder to take an electron from? K, why? Because K is smaller, all right? K is smaller because of N. Let me skip C, let's do D. K and K plus, which one is it harder to remove an electron? K plus, why? Because K plus is smaller. It's smaller, K plus is smaller. So it's harder to take the electron from it. And then, okay, remember the reasoning we're using for all of these, then which one of these is it harder to remove an electron? Cl or Cl minus? Cl, why? Because it's smaller. Anions are always bigger, all right? So yeah, that's the trend. So let's do the one that I skipped, all right? So notice that A, B, C, all of the ones except C, the answer pointed to the thing that was smaller. But this kind of breaks down with C. It's a special case where we're removing an electron from sulfur and phosphorus. So at first glance, when you look at sulfur and phosphorus, let's circle those. Which one do you think it's harder to remove an electron from? Sulfur, because it's smaller, but it's actually the other one. Phosphorus actually has a higher ionization energy, and this one is an exception, right? And so I'll draw out that exception for you, right? So and this is what I call the 5a, 6a exception. So a 5a element, its electron configuration looks like this. 5 valence electrons, so 1, 2, 3, 4, 5. But a 6a element, it looks similar, but just 1 extra electron. So let's draw that out. All right, so we have 6 electrons. 1, 2, 3, 4, 5, 6. All right, so we have the choice to remove an electron from a 5a element and a 6a element. So I like to think about this, my analogy, it's like if you've ever watched the show Dance Moms, and one of the moms has to make a cut off the team, all right? Or just imagine like you had to make any cut off of a dance team. And what I mean by dancers are these electrons that are spinning in opposite directions. So notice this 5a example, all right? We have some electrons spinning in opposite directions, okay? That's nice. And then we have a bunch of electrons all spinning in the same direction. So is it obvious where I should make the cut off this team? It's going to be kind of hard, right? Because there's a lot of, I guess, like symmetry involved here. But then look at this 6a example. Do you see a more obvious person, a more obvious electron to cut off the team? Which electron? This one, right? Why is that one going to get cut? Because it's spinning opposite of all the other ones. So if this was a dance, team and, all of your electrons are supposed to be spinning the one way, one spinning the other way, it's easy to pluck that one off. So what we see here is that this electron is actually fairly easy to remove, all right? So this 6a element all 6a elements have slightly lower ionization energies than these 5a elements. These are actually hard to remove. All right, and so that is a small exception here. So our answer here is phosphorus is actually the harder one to remove because of this 6a, 5a exception. You would think it would be sulfur because it's smaller, but it's not because of electron spin. So same thing, all 5a, 6a elements work this way as well. So nitrogen and oxygen, if we were comparing those two, you might think, oh, oxygen's harder to remove, it's smaller, but it's actually not in terms of ionization energy. We see here that nitrogen is harder to remove an electron because of that whole spin pairing thing, all right? So that is a small exception. And it happens between 5a and 6a. It also happens between 2a and 3a elements as well. I'll show you that example as well. All right, you would think that boron is harder to take an electron off of. But let's just draw out this example. So a 2a, 3a example. So the Dance Moms analogy still works. All right, so here is a 2a element. You think it's easy or hard to make a cut off this team? Hard, because they're all spinning opposite directions. But what about this one? Really easy. What electron are you taking off? That p electron, all right? So what we see here is that our 3a elements have just slightly lower ionization energies than predicted because of this like lonely electron. All right, okay, so what we see here is that ionization energy trends with size, where small things typically, 95% of the time, the smaller thing will have the higher ionization energy, harder to remove an electron. So the last idea here is electron affinity, so energy associated with adding an electron to it. So adding an electron to an atom sometimes is exothermic, meaning it's favorable, but sometimes it's endothermic, meaning it's unfavorable. So in this case, I want you to tell me in which case is it favorable to place an electron on the thing. So I want you to tell me which one has the most negative electron affinity associated to it. So what we see here is that really favorable electron affinity reactions happen when your electron is really attracted to your atom, right? So the more attracted your atom or your electron is to your atom, the more energy that is released, the more favorable it is, right? So your electron is going to be really attracted to the nucleus when it's either close to the nucleus or when Z effective is really high. But what we're actually going to look for is size, because typically particles are really small when either your N value is low or Z effective is high. So in the end, if you're able to place that added electron really close to the nucleus, then a lot of energy comes off. So really this trends with size for the most part, where smaller the size, more favorable the electron affinity. So let's look at these. All right, O and F. Okay, so let's look at my periodic table down here. I'll move you over here. All right. Oh yeah, there's the trend. The smaller thing typically has the more favorable electron affinity. So oxygen and fluorine, right? Think about it this way. Notice that both of these elements are in the same period. So they're, what we typically look at in terms of size is their Z effective. So the Z effective for oxygen is +6. For fluorine, it's a +7. So if you're a dumb little electron, where are you more attracted, +6 or +7? +7. So if you go to that +7, more energy is going to come off because you're way more attracted to it. So that means fluorine has the higher effective nuclear, sorry, the more favorable effective nuclear charge. We're actually looking for the more negative number in this case. Right? And so if we want to show a reason here, why does fluorine have the more favorable electron affinity? The reason is because F is smaller. Why is it smaller? Because of Z effective. All right, the next one, O or O minus. Which one is it more favorable to place an electron on it? O, why? It is smaller. Also think about it this way. Okay, we have an electron, and you want to add it to this O minus. What kind of interaction is that? That's repulsion, all right? Because you have two negative things that you're trying to jam together. So actually adding another electron to O minus is actually unfavorable. Adding the second electron, that's what I'm trying to do here, is actually endothermic. It requires energy to do it, all right? All right, next one, S or SE? So S, SE, which one is more favorable to add an electron? S, why? It's smaller, very good. And finally, this one, K or K plus, which one is it more favorable to add an electron? Why? It's smaller, right? So what I want to get at here is that you get a lot of energy back when you place an electron really close to the nucleus. If it's really close, it's typically that valence shell is very, very attracted to that negative electron, and that's why a lot of energy comes out. That's why it's favorable. So in the end, the trend is the smaller thing in the end, if that helps you. Okay. All right, so now let's put it all together. Let's consider these atoms, order them in increasing radius. So we got to kind of put all of the stops here. Remember, we look at N value, we look at Z effective, and sometimes we also look at isoelectronic things. So what I want to do here is look at the N values for all these things. All right, so notice we have K plus. So if we look at K neutral is an N equals 4 electron. But if we remove 1 electron from potassium, we have 18 electrons. So K plus is actually an N equals 3 element because there's only 18 electrons there. Do you see how I got that? Right, if you look at the periodic table right here, okay? If we start at K but remove an electron, we move up to argon, and that's N equals 3. Right? This is important because this can allow us to get a rough idea of where our things are. Okay, so then chlorine minus is N equals, what is that? N equals 3, calcium 2 plus, right? Where we start at calcium but remove 2 electrons. This is also N equals 3. because it has an argon electron configuration. Maybe I'll just write that down here. K plus is argon, calcium 2 plus is argon. And then finally, rubidium, this is an N equals 5 element. So based upon this, we can actually deduce the largest element or the largest particle right off the bat. Which one's the largest? Rb. And then actually, we can get the second largest as well. What's that? K, perfect. And the reason, it's because it's N equals 5 for Rb, and N equals 4 for that one. So what we're gonna see is all of the N equals 3 ones show up here, right? All the N equals 3 ones show up here. And then there's actually something special about all of those N equals 3 electrons. All of them have the same electron configuration. All of them have 18 electrons in them. So that was a special case with size. What did we call that? Isoelectronic. They all have the same number of electrons. So what do we look at if they all have the same number of electrons? Protons. So you have 18 electrons surrounding a plus 19. Chlorine, you have a plus 17. And then calcium, you have a plus 20. So of these, which one is the smallest? Which one are your electrons really attracted, the most attracted to that nucleus? Calcium, all right? So yeah, it's gonna be the calcium 2 plus is the smallest. Next, it's gonna be the K plus, and then it's gonna be the chlorine minus, all right? And so that is a special case where all of these N equals 3 particles, they all have the same number of electrons. All right, last couple for 7. Okay, so this last one. What shows the correct successive ionization energy for gallium? So let's look at gallium on the periodic table. Here. All right, so notice that gallium, let's erase some stuff here. Gallium is right here. When we think about gallium and its position on the periodic table, it's in group 3A, it's under aluminum. So gallium has how many valence electrons in it? 3. So 3 valence electrons means that 3 electrons are fairly easy to remove off of gallium. But removing the 4th electron off of gallium is gonna be really, really difficult. So here are a bunch of energies of removing 1 electron after another. So this first graph is kind of showing, oh, you have an element where you can remove the 5 electrons fairly easily. This indicates an element with 5 valence electrons at least. So A is not the correct answer for gallium. Right, and this one, you can remove 5 electrons pretty easily. What about, okay, there's 2 Ds, interesting. This is what happens when I make stuff from scratch. All right, what is graph B trying to show us? An element with how many valence electrons? 2, because you have 2 low energies, and then it jumps up. It's really hard to remove that third electron. So this has 2 valence electrons. So this isn't the correct one for gallium. It might be the correct one for like calcium or magnesium or something, but not gallium. All right, what about C? It looks like, oh, there's 3 low energy electrons, but don't C and D look kind of similar? See how both of them have 3 low energies and then the last 2 are high? There's a difference between C and D, and what is that? C, the energies go up, the second energy goes up, but then the third one, it goes down. What do we know about making a cation? We know we remove an electron, we make a cation. Remove another electron and make a 2 plus cation. When we think about the size there, like if we did calcium, calcium plus, calcium 2 plus. Of these, which is the largest thing? Calcium, and then what's the smallest thing? 2 plus. So when we think about successive ionizations, it always gets harder and harder and harder to remove the next electron. The reason is because the cation keeps getting smaller and smaller and smaller. So C is not right. And the reason is because it cannot be easier to take the third electron off than it is the second one. Does that make sense? So that's why D is the correct one. We can't have the energies kind of fluctuate up and down. They have to get harder and harder and harder. But the takeaway in these graphs are, where is that big jump happening? When are you pulling electrons out of a inner shell, right? So the correct answer is D. All right. Okay. Oh my gosh. Why is chapter 7 taking so long? Okay. So this last one, what is the reverse reaction of the first ionization energy of titanium? So we kind of have to do some reading comprehension here and really understand what does this mean. So I'm going to just write what is the first ionization energy of titanium. We're going to start with titanium. Ionization energy means we're doing what with the electron? We are removing it. So our reaction is titanium neutral, and we're making a titanium plus, right? That's my reaction. That's the first ionization energy of titanium. But in this case, we are looking for the reverse of this reaction, all right? So we are looking for which reaction describes T plus combining with an electron to give T regular here. Right? So let's think about this reverse reaction. Let's just write it out. Ti plus an electron gives us T regular neutral. So notice that this reaction, the electron is now the reactant. So are we still talking about ionization energy here? No, what are we doing to this substance? We are adding an electron. So this is actually electron affinity. Okay, but it's electron affinity of what? What are we adding the electron to? Are we adding the electron to a titanium neutral atom? Nope, we are adding it to a Ti plus. Okay, I think even I messed this up when I was in undergrad. I thought ionization energy was the reverse of electron affinity. It's not quite. All right, because what we just proved here is that the reverse of the first electron affinity of titanium is actually the electron affinity of T plus. It is not the electron affinity of Ti regular, because what that would look like this. Ti with no charge plus an electron gives us Ti minus. Ask yourself, is this the reaction? The reverse of the target reaction here? They are not reverses of one another. The reactants and products are slightly different. So the answer here is the electron affinity of Ti plus. So do make sure you get those charges right. All right. Okay, so let's do a little bit more here. All right, basics in chemical bonding. So chapters 8 and 9 really explores ionic substances, molecular substances. So the first thing we looked at in chapter 8 with bonding was ionic substances, the bonding in ionic things. So to do this, ranking ionic compounds in order of increasing magnitude lattice energy, what you need to know is that lattice energy, it trends like potential energy, all right? Lattice energy is large when the charges involved in your ionic compound are large, or when your ions are small, right? So what you want to look at here for these things to determine lattice energy is you always look at the Q1, Q2 product first. If your Q1, Q2 product are the same, then you want to look at your ion sizes, where ions that are small have large lattice energies. The reason is this equation. Just think about this. If you put a big number in the denominator, what kind of number comes out? Small. But if you put a small number in the denominator, what kind of number comes out? Big. So what we see here is that small ions have large lattice energies. Large ions have smaller lattice energies, all right? I promise you'll make this mistake. But just remember this equation. We always look at the Q1, Q2 product too, but when we look at size, small size has large lattice energy because D is in the denominator. So let's look at these examples. I always get the Q1, Q2 product first. So just go through the charges. So here, sodium and iodide is +1, -1. Magnesium chloride is +2, -1, where notice I'm only looking at one of those chlorides. Calcium sulfide is +2, -2, and then NaCl is +1, -1, all right? So of this, what we've shown, I can right off the bat tell what is the largest lattice energy, and that one is going to be the calcium sulfide, all right? Calcium sulfide is going to have the largest energy because the charges involved are the largest. Actually, maybe I should just define what is lattice energy first. It's the energy to rip apart your ionic compound. So if we start with a salt, a cation and an anion, we are estimating what is the magnitude, the energy to rip apart those ions from one another. So if we start with a +1 -1 or a +2 -2, just think about magnets. Is it harder to rip apart a +2 -2 or a +1 -1? It's going to be +2 -2. So that's why we're looking at the magnitude of the charges first. Can we get the next largest as well? Yes, we can. It's going to be MgCl2. All right, but now we have a problem. Notice that both of the last ones are +1 -1 charges. So this is where we're going to look at size. And what is the trend? Small size means large lattice energy. So notice that both of these options have NAs in them. So we can ignore that. We're going to look at the anion. Our choices are iodide or chloride. So iodide's the larger anion. So which of these has the larger lattice energy? NaI or NaCl? NaCl. Why? Because Cl is smaller. All right, and so that's the order. Right? So always, oops, I wrote it twice. Yes, okay. Always do Q1, Q2 product first, and then do size if they're the same. Okay, perfect. All right, so that's a conceptual thing of lattice energy. So the next part here is, well, what is lattice energy? Lattice energy, again, is the energy to rip apart your ions, all right, from the gas phase. Lattice energy is this 7th step in the Born-Haber process, all right? This step is the negative of your lattice energy. Notice that, what was I saying lattice energy is? It's the energy to rip apart your ions. Notice what's happening. We're starting with calcium chloride solid. We're ripping it apart into its free ions. So the upward arrow here is lattice energy, but in the Born-Haber cycle, we get that energy back when those ions come crashing together. This is what you need to get out of this, Born-Haber cycle. So here I'm just being, conceptual. Let's describe each step of the cycle. All Born-Haber cycles look the exact same, where the step in the bottom corner right here, this is always delta H of formation of the salt. Like, remember in chapter 5, this could be a chapter 5 question where I ask you, what is the delta H, what is the equation for the delta H of formation for calcium chloride? All right, how did we get delta H's of formation? We took the elements in their most stable state and formed 1 mole of that product. So if I asked you, how would you write this equation, the delta H of formation of calcium chloride? The first reactant would be what? Calcium solid. This was back in chapter 5. We already assessed you on this, right? And then what else is in this compound? Chlorine. So you ask yourself, what is chlorine in its most stable state? Cl2, and it's a gas, all right? And then we make sure it's all balanced, which it is, right? So notice that that is what this first step describes. Look, calcium solid plus Cl2 gas gives us calcium chloride solid. That's delta H of formation. It almost always shows up in this bottom corner. So we're just thinking what individual steps gets us from elements in their like neutral, most stable state over to ions in the gas phase to then finally get our salt. So if we go through these steps, the first step, delta H of formation, this one right here, right? We're gonna still end up at delta H of formation, calcium chloride solid. It's just, we're just gonna go about it a different way, right? And that's the, great thing about Hess's law. We don't have to, we can just add up reactions to get an overall reaction. So notice what is happening in this first step. Look and really focus on what is changing between those two lines. Calcium solid is turning into a gas. What is that process called, solid to a gas? Sublimation. So this first step is sublimation of calcium solid. That's what that first step is. Okay, let's look at this third step. What's changing between this line and this line? Focus. What changes? It's like the highlights book. It's like, what's different about these two pictures? What's different about these two things? Cl2, let's highlight a different color. Cl2 is becoming what? 2 chlorines. How do we achieve that? What property is that called? Bond breaking, bond enthalpy. So this third step is the bond enthalpy, or the bond breaking of Cl2. Okay, we broke that chlorine-chlorine bond. Is that something you could look up in a book? Yeah, we literally had tables on it that we looked at in chapter 5. All right, what is the next step? What is the fourth step? So look very closely. What is different between this and this? You have a calcium, different color, calcium neutral becoming calcium plus, and then you have that free electron. What do we call that? Ionization energy. Yes, ionization energy of calcium. Specifically, which ionization energy? The first, the second, the third? It's the first, because then what is the next step? That one is the second ionization energy. How do I know? What's changing is we're going from calcium plus to calcium 2 plus. So we've already taken that first electron off. Now we're taking the second electron off. All right. So now we have calcium 2 plus and 2 free electrons just floating around. So the last step here is those 2 electrons are going to associate with those 2 chlorine atoms, producing chloride minus. So when we add an electron to chlorine, what do we call that? Electron affinity of chlorine. Perfect. And that's what all those steps are. All Born-Haber cycles will look very, very similar to this, right? So when calculating this, this is how I like to do it, is I recognize that delta HF is my focal point, and I'm just taking a different route to get to the end. So how I like to do this is delta H of F is equal to all of the steps until we get to the ions in the gas phase, and then we subtract lattice energy. So in this example, delta HF, or delta H of 1, is equal to delta H2 plus delta H3 plus delta H4 plus 5, 5 plus 6. So notice that adding all steps from 2, 3, 4, 5, 6 brings us to ions in the gas phase. And then where lattice energy comes into play, it's this last step. And so you always subtract lattice energy. All right? And that's the equation to calculate lattice energy of any substance using the Born-Haber cycle. It's always delta HF of formation is equal to all of the steps that lead up to the ions in the gas phase, and you subtract lattice energy, right? So, these steps could be like 18 different steps if needed, right? Doesn't matter, you just add all of them up and then subtract lattice energy. So if we want to actually calculate lattice energy, look, we have numbers for every single thing. Every single thing, we're just solving for lattice energy. So you can literally just plug in those numbers. Negative 790 equals 178 plus 242 plus 590 plus 1145 minus 698. Notice that step 6 is exothermic, and then minus lattice energy. And so just solve for lattice energy. If you have that minus sign there, then you ensure that lattice energy comes out to be a positive number. And if I actually show that, I realize I need to go a little faster here. Lattice energy, when you calculate this, is a excuse me, pretty big number, 2,252 kilojoules, right? And so notice here, if you subtract lattice energy, this is how you force that number, the number to come out as a positive number. But notice in the Born-Haber cycle, step 7 is an exothermic process. You're doing the reverse of lattice energy. All right? So it's just as important to do the math as it is to understand the process, the concept behind this Born-Haber cycle, all right? So this is the last time we'll need our calculator. All right, so, okay, let's now move on to covalent bonding. So here, all right, without using an electronegativity table, but you can use a periodic table, so I'll just bring that down here. Cut. Let's use a periodic table here. Okay, paste. Without using an electronegativity table, rank the following bonds in order of increasing polarity. So that means we are ranking these in order of difference of electronegativities of these two atoms that make up this bond. So the tricks for electronegativity using the periodic table, it trends this way. All right, fluorine is your most electronegative element with a electronegativity of 4. Cesium is the least electronegative element. And so that means electronegativity increases going towards fluorine, decreases going towards cesium, right? So what we see here is that elements that are really far away from one another on the periodic table, if you put them together in a chemical bond, it's going to be a really polar bond. Maybe so, where let's say we combined like potassium and chlorine. Notice how they're super far away from one another on the periodic table, right? Where their electronegativities are so different that the electron completely transfers from potassium to chlorine. That's called an ionic bond. Think about KCl. What kind of compound is that? An ionic compound. So that makes sense that when you have a really not electronegative metal and a very electronegative nonmetal, that's how you make ionic compounds. But you know, there's a really rich chemistry with all nonmetals that we can still have slight polarity in our bonds even when everything's a nonmetal. So my second tip is fluorine is the most electronegative element, but oxygen, chlorine, nitrogen, and bromine also have very high electronegativities. They're all very high. They're all basically above 3, all right? So I call those 5 the high 5, meaning that they have high electronegativities. So if you bond anything to an oxygen, it's going to be really electronegative, like a carbon and an oxygen, a sulfur and an oxygen. You're going to make a really polar bond because oxygen has a very high electronegativity. Same thing with anything in the high 5, all right? But if you bond something in the high 5 to something else in the high 5, will it have a large difference in electronegativity? No, not if both numbers are very high. And that's very useful, and that's going to be useful here, all right? Because of these 3 things, one off the bat we should get right away. What is the electronegativity difference in this molecule right here, or this bond? 0. So this bond is going to be completely nonpolar, right? So now we need to decide which bond is more polar, OS, or OF. Those are our options. So when we look at these options, you know, if you look at them, you might think, oh, they're like, you know, right adjacent to each other on the periodic table, so it's kind of difficult to tell which one has the larger difference. But if you have understanding of the high 5, all right, O is part of the high 5, right? So if we bond it to S, do you think that electronegativity difference is going to be big or small? Is S part of the high 5? So when you take the difference is going to be big versus O and F. O and F both have high electronegativity, so the difference is going to be small. So the most polar bond is going to be O and S, and of the other one, O and F is going to be in the middle. All right, that's how we're able to get that. That one's definitely tricky because you have to have understanding of kind of some of the numbers of the periodic table. I always remember fluorine is the most electronegative, and then those other 4 are part of the high 5, and that usually gets me out of most trouble when it comes to electronegativity. But sometimes it can be a lot more straightforward. Like here's an example. If you have a CN bond versus a CO bond, which one's going to be more polar? CO, yeah, because those elements, they're further apart from one another. CN, CO, CF, which one's the most polar? CF, yeah, because the elements are even further apart on this table, meaning that how electronegativity changes will be more, so the difference will be more, all right? So that one has like a different kind of thinking to it that isn't as tricky, all right? Dipole moment. Yeah, okay. So let's talk about dipole moment. This is the other equation that's given. Dipole moment equals Q times R, right? We will never ask you to calculate the numerical value of dipole moment, but you need to be able to use this equation to just see trends, all right? How numerically can dipole moment increase? When Q increases, dipole moment increases, or when R increases. So what does that mean about a chemical bond? It means if Q increases, really what we're changing is delta En. So what I'm trying to say is dipole moment for a bond increases when you increase delta En, which makes sense. A bond is more polar when the difference in electronegativity is greater. But here's the difference, is that dipole moment also has this R component to it. So what this also means is that mu, or dipole moment, will increase when your bond length increases, right? So either of those things will increase your dipole moment, okay? So let's look at this example. I tell you that the dipole moment of NH is 1.5, but BRH is 2.6, all right? And I want to know why. Why is the HBr bond more polar, have a larger dipole moment than NH? Notice how I give you electronegativities here, right? So since I know dipole moment has to do with delta En and bond length, let's calculate. What is the delta En of these different bonds? So of N and H, let's take that difference. N is 3, H is 2.2. What is that difference? 0.8. And then what about in our BRH bond? What is that difference? 0.8. So I ask you, when you calculate dipole moment for these two bonds, does Q explain the difference? No, why? Delta En is the same. So what has to be the reason that these dipole moments are different? Has to be the R component. And so if we look at these two statements, why is the Br bond more polar? It's because, not because the electronegativity differences are, different. They're actually the same. They're the same. They cannot explain the difference. It's because bromine is a larger atom than nitrogen. So that means that R increases is larger for that HBr bond. All right. So the correct answer is 2. That one's definitely tricky. Here's another example. All right. What if I had these two bonds, NO and double bond O? Can you tell me which one has the larger dipole moment? The single bond or the double bond? Are you sure? Okay, so let's remember the equation for dipole moment is Q times R. Is Q going to help us here? No, why? Delta En is the same. But Dr. N, you didn't tell us what delta En is. It doesn't matter. I just know that they're the same. So that's not going to be the differentiating thing here. So R is the reason that there's going to be a difference in dipole moment. But what's the trend in R? Does a big bond or a small bond have a large dipole moment? Just look at the math here. If you put a big number in R, a big dipole moment comes out. So the correct answer is actually the single bond has the higher dipole moment. Why? Because R is larger, the bond is longer. All right, so that's another example. Okay, let's keep going. Let's complete the Lewis structure for this molecule, so all atoms obey the octet rule. So what we'll learn here is that there's a handful of elements that follow the octet rule really well. Hydrogen, carbon, nitrogen, oxygen, fluorine. Those are like our magic elements. They always behave very, very similar. Based upon the Lewis dot structure, hydrogen has one unpaired electron. So typically hydrogen makes one bond. Actually, I'm just going to straight up say hydrogen will always make one bond because there's one unpaired electron. But if you draw the dot structure for carbon, you have 4 bonds or 4 unpaired electrons. So carbon will make 4 bonds. Nitrogen, on the other hand, when you draw out its Lewis dot structure, How many unpaired electrons are here? How many of them are unpaired? 3. So nitrogen makes 3 bonds, leaving 1 lone pair. So that's what a nitrogen atom typically will have. Oxygen, it's a Lewis dot structure, so notice that there are 6 valence electrons on oxygen. So oxygen will make 2 bonds, 2 lone pairs. And then finally, fluorine has 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. So based upon that structure, how many bonds will fluorine make? 1 bond, and I'll have 3 lone pairs. If you know this, and you know the general conductivity of a molecule, you can fill out a really complex molecule just following these rules. So let's see what's going on here. So I'm trying to show you the conductivity. All right, so let's work left to right. The first atom we have is a nitrogen, and there's 2 hydrogens attached to it. How do I know? Because it's NH2. That nitrogen is attached to a carbon. That carbon has 1 hydrogen attached to it, right? So that first carbon is attached to another carbon. And that carbon has how many hydrogens on it? 1. So let's keep going. The next carbon has 2 hydrogens. And then finally, we have an OH bond, okay? So there's just like a rough skeleton structure. So what a lot of students might do is just like, start counting number of valence electrons, completing octets. We can do that as well. So notice here, look at nitrogen. Does it have a complete octet? It does not. So some students, they might try to make a double bond, but let's go back to its Lewis dot structure. What does nitrogen usually have? 3 bonds and 1 lone pair. So do you think it makes sense to make a double bond here? No. How should I complete the octet of that nitrogen? Instead, I should put a lone pair. All right? What about this carbon? Does it have a complete octet? No. What about the carbon next to it? No. So they both need an extra bond. So I can, boom, just draw that in. So now I completed the octet of both of them at the same time. All right, so then let's look at this carbon. Does this carbon have a complete octet? Yes. What about this oxygen? No. So should I draw more bonds to oxygen? No. What am I going to do? Draw more lone pairs. How do I know 2? 1 to complete the octet, but that's also what the Lewis dot structure says. Okay. Okay, so let's do this next one. Select all the molecules whose central atom violates the octet rule. So the unfortunate thing here is we just have to draw them. We have to draw them. So I'm actually going to just open up a new page. We got to draw them. So the rules to the octet rule, or Lewis structures, right? Lewis structures follow 6 rules. And if you master those 6 rules, you will always be right. You will absolutely know when to put double bonds, multiple bonds in a molecule. It's not about spraying and praying electrons on your structure. You can exactly know how many electrons you place. So those rules are, you want to count how many valence electrons each of your atoms contributes. So for BF3, you count the number of valence electrons. Boron contributes 3. There's 3 fluorines that contribute 7. And so if you add that up, we can place 24 electrons, right? So that's the first step. If you have something that's charged, like an anion or a cation, you will add or subtract electrons from your count appropriately. Next, you draw your skeleton structure, where usually the first element written in the formula is your second, or is your central atom, and then you draw your connectivity, meaning just drawing single bonds to everything. So we have fluorine, 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 right? So notice I used some electrons to make bonds, make single bonds. So single bonds contain how many electrons? 2. So that means how many electrons have I placed on this structure so far? 6, I can spend 24. I have to spend 24 total. So I'm going to use up the rest of those electrons by placing electrons on the outermost atoms, working my way into the central atom if I have any electrons left. So let's do that. So I have 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So I ran out of electrons. That means I do not place any electrons on that central boron atom. This is the final structure of BF3. You might be looking at this saying, oh, but boron is octet deficient. That's okay. Boron can be electron deficient. It's okay. So the things that can violate the octet rule are boron, because it can be octet deficient. Also, where's my periodic table? Did I lose it already? Where did it go? Dang it, I lost it. Boron can violate the octet rule by being electron deficient, or any element in period 3 or heavier, all right? So let's draw the rest of these. BRF3, so same idea. We go through the steps. How many valence electrons are we allowed to place? Bromine and fluorine have 7 electrons each. There's 4 of them, so we can place 28 electrons. Right? That's how many we can spend. We place the bromine in the center. We place the fluorines all around it. Next, we count very carefully and complete the octets of the fluorine. If we have any left over, we place them on the central bromine. Count very carefully. I remember in high school, I would just spray and pray my electrons, and I didn't know when to stop. I literally didn't know, all right? But here, if you count carefully, you know when to stop. So how many electrons have I drawn so far? 6, so 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So that means how many lone pairs go on that bromine atom? 2, right? It's not about memorizing. It's not about any of that. It's all about just following those 6 steps. So is there anything wrong about that bromine's octet? Yeah, it's also it's exceeded its octet. Is that allowed? Yes, it is allowed, because bromine is a period 4 element. So this is allowed, this is allowed. So I guess going back to this, both of these have exceeded octets, right? What about CF4? What is that going to look like? So if you go through the 4 steps, it's going to look like this, right? And then all the fluorines have complete octets. Does carbon violate the octet rule? No, so we don't have to choose that one. So let's do the next one. We have 2 selenium examples. So you might look at selenium and go like, oh, selenium is in period 4. So both of those violate the octet rule, but actually only one of them does. So let's actually draw them. So we have 2 options. We have SEF2 and SEF4. So let's draw them. Selenium F2 has 6 plus 2 times 7, I think that's 20. And then the other one has 6 plus 4 times 7, I think that's 30 what? 34? Right? So let's draw this. So selenium's in the middle, 2 fluorines. All right, so that's 4 electrons. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I put 2 lone pairs on that central selenium. Does that selenium violate the octet rule? No, it actually, it has 8 electrons, so it's good. That one's good, right? But then if we do the other one, selenium with 4 fluorines, right? 8 electrons placed so far. So 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. So 1 lone pair goes on that central selenium. Does that selenium violate the octet rule? It does. Is that okay? Yes, because selenium is in a group whatever. It's in group, or it's in period 4. So notice, selenium can exceed its octet, but does it always have to? No. All right, so just because an element can exceed its octet doesn't mean it has to. So the answer for this question, once you draw them all, is those four. All right, so selenium in SEF2 does not exceed its octet. Okay, let's go through these a little bit faster. Let's look at this example. I'm just gonna draw these for you because I don't feel like drawing them or going through all the steps. So CO2 looks like this. Carbonate, or sorry, I'm gonna do carbon monoxide here. Carbon monoxide looks like this. And then carbonate is special and it looks like this. Okay. So I want you to tell me what's the order of these bonds in increasing bond enthalpy between the C and the O atoms. So if we want bond enthalpy, this is basically strength. That's what we're looking at. What is the strongest CO bond? What is the weakest CO bond? So what we're gonna do here is calculate bond order for all these CO bonds. For a lot of them, the CO bond order is really obvious. So like this one. What kind of bond is between the C and the O and carbon monoxide? A triple bond. So the bond order is 3, right? So in this example, the triple bond is localized in one place, so the bond order is 3. Use that same idea. Look at the CO bonds in the carbon dioxide molecule. Notice that they're identical. So each of those CO bonds have identical bond orders. And what is that bond order? 2. All right, so of these two examples, we can clearly see which is the strongest bond. It's the carbon monoxide because it's a triple bond. It's a bond order of 3. So now we need to decide, where does carbonate fall there? Because if you look at carbonate just right off the bat, it kind of looks like there's double bonds and single bonds in carbonate, right? But does that double bond only exist in this position? It doesn't. It actually exists in all 3 positions at the same time, because I just chose to finish the Lewis structure this way, but I could have put that double bond in any one of those positions. So when it comes to bond order for resonance structures, this is how I like to think of it, is this double bond can go here, here, or here. So I have a double bond swapping places with a single bond and another single bond, but it's not swapping places. It's actually smeared across the entire molecule. So we have all those bonds swapping 3 different positions. So if you do this, that math, 4/3 has a bond order of 1.33. So what we see in carbonate, if we actually measured the bond strength, is we would find all identical CO bonds that are slightly stronger than a CO single bond, all right? So if we order these, this one is going to be the weakest, and then CO minus is going, or sorry, CO carbon monoxide is going to be the strongest, right? So definitely watch out for those bond order things. Okay, let's do formal charges. All right, so there's a strategy for formal charges. It's a way we can deduce which is the most dominant Lewis structure. So my trick to formal charge is, we're going to calculate the formal charge of every single atom in each of these structures. So to calculate formal charge, I think, how many valence electrons does each of those atoms want in its valence shell? Right? So like nitrogen typically has 5 electrons in its valence shell. Oxygen has 6, right? And then we want to subtract how many electrons are actually assigned to that atom in the structure. So what does that mean? It means if I zoom up on this molecule, all right, Notice that this nitrogen has 6 electrons in lone pairs, but one of those electrons come from that chemical bond. So what I tell my students is when you're doing formal charges, take all of the bonds in your molecule and make them go get a divorce, meaning the electrons go back to their original atom. So this bond has 2 electrons, make one of the electrons go to that nitrogen, make the other one go there. They're all getting divorced. So then this triple bond has a total number of how many electrons? 6. So how many of them get assigned to this nitrogen? 3. 1, 2, 3, and then the other 3 go to this oxygen, right? So when all the bonds get a divorce, then it's really easy to just draw a box around every atom and be like, oh, those are the electrons assigned to each of those atoms. So when we calculate formal charge, we're gonna take the number of valence electrons typically on that element, and we're gonna subtract the electrons in the structure. So all the electrons that are in that box. So nitrogen typically has 5 valence electrons, 5, 6, but in the structure, how many electrons does this nitrogen have? 7, and then the middle one has 4, and then that oxygen has 5. So if we subtract these numbers, we get that first nitrogen has a -2 formal charge. It has 2 extra electrons. It actually doesn't want them. The middle nitrogen is +1, and then that oxygen is also +1. So is that a good Lewis structure? It's not, because it doesn't minimize formal charges, right? So let's do the same thing to this one. Make all your bonds go get a divorce, right? So it's number of valence electrons minus the electrons that are on that atom. So it's still 5, 5, 6, but how many electrons are on that first nitrogen? 6. Then how many on the middle nitrogen? 4, and then on the oxygen? 6. So the formal charges here are -1, +1, and what? 0, right? And then let's do the last one. So it's still 5, 5, 6. So how many electrons are assigned to this first nitrogen? Remember, all the bonds go under divorce. So I'll draw it in like this. So how many electrons on that first nitrogen? 5, and then the middle one? 4, and then the last one? 7. So when we do this subtraction, it's 0, what is that, +1 and -1. Okay, so which structure can we eliminate right off the bat? That first one. So let's look at the second and the third one. Because notice there's slight differences. Because in neither of them, we've minimized formal charges. This is kind of as low as we can get. Like we have to have some minus and plus present. So let's focus on the difference between these two. In this structure, I place the negative formal charge on a nitrogen. On the third structure, I place that negative formal charge on that oxygen. Which of those elements will accept that negative charge more, the nitrogen or the oxygen? Oxygen, why? It's more electronegative, yeah, so the correct structure, the most dominant structure is gonna be this last one, and it's because the negative formal charge is on the more electronegative atom, oxygen, right? So here we have a choice. We have to have a negative formal charge. If I have a choice, I'm gonna put it on the atom that is the most electronegative. I don't wanna put it on nitrogen, I wanna put it on oxygen. All right, dang, we got 30 minutes left. So let's do, okay. We can do this quickly. Okay, it's all the structures that take a long time. Okay, let's draw the Lewis structure of BF3. We already drew this guy, didn't we? Right? Boron's in the middle. We have 3 fluorines. We complete the octets. What's special about boron? It can be octet deficient. So is this the correct Lewis structure? It is. So boron is allowed to have that, to be octet deficient. All right, so that's the Lewis structure. We draw it earlier. So given the structure, what is the electron domain, electron geometry about that central atom? So our strategy here is you look at that central atom, count how many electron domains are around it, It's 3 electron domains. Oh, I have all these models and I didn't even use them, right? It's because I'm sitting. So the idea here of VSEPR theory is that electrons, they're negatively charged, they will always repel one another. So when you have a certain number of electron domains, the shape is dictated by how can you effectively spread out those electron domains so they maximize their distance away from one another. So if you have 3 electron domains, what's the maximum, what's the shape that those domains adopt? Trigonal planar. Yes, if you have 3 domains, they will position themselves so it's trigonal planar, so it looks like this. They're all 120 degrees away from one another. All right, so the next one is, what is the molecular geometry of the central atom? So to get molecular geometry, take into account lone pairs, right? Because can we see lone pairs? We can't. So to get molecular geometry, you consider where are those lone pairs at, and then you want to cover them up because you can't see them. So the molecular geometry for BF3, do we have any lone pairs to consider? No, so the geometry is going to be the exact same, right? Because there are no lone pairs. All right, what's the predicted bond angles for BF3? This comes from your electron geometry, so 120 degrees. Right? Okay, this is a little bit of chapter 9, so 8 and 9 are kind of mixed together. What is the hybridization of that central atom? So this is like sp or sp2, sp3. So the trick I tell my students is to understand hybridization. Look at the number of electron domains of your central atom. That number is equal to the number of atomic orbitals you hybridize. And that is also equal to the number of hybrid orbitals you get out. So what does that mean? Well, this boron has how many electron domains? 3. So then how many atomic orbitals should I hybridize? 3. So what letter designation does that have? So I like to think of it this way. All right, so in like a normal atomic orbital, you have an S subshell and a P subshell. So if we want to combine 3 of those orbitals, so just read it left to right. We want to combine an S orbital and 2 P orbitals. So we call this sp2 hybridized, right? I mixed 3 atomic orbitals because there are 3 electron domains around that boron atom. So this is sp2 hybridized, right? Okay, next, do we think this molecule is polar or nonpolar? So think about these really electronegative fluorine atoms, but also think about the bond angles between these. They're all 120 degrees away from one another. So when we have really polar BF bonds pulling on that central atom, they're all 120 degrees away from one another. All of those vectors cancel. This is a nonpolar molecule, right? And then finally, using valence bond theory, what 2 orbitals are involved in the bond that makes the BF bond in this molecule? So this is definitely a tricky question, but what I ask students is, you already told me the hybridization of this boron atom. That's telling me where that electron is that makes up that bond. So really what this question is asking is, what 2 electrons make up this bond? One of these electrons is that sp2 electron that we talked about in hybridization. This electron on this fluorine atom comes from a p orbital, right? So what valence bond theory says is we can't just think about electrons being dots that combine to make Lewis structures. We need to think about what orbitals are overlapping in 3 dimensions to make this chemical bond. So the answer here is boron's unpaired electron is coming from an sp2 hybrid set, and it's overlapping in space with a fluorine's 2p orbital. All right, so what that would look like is this. All right, here's that sp2 hybridized set, and then here is a overlapping p orbital on fluorine. And I ask you, if I overlap these 2 things, that is a sigma interaction, that is a single bond. All right, so that's what valence bond theory tells us. Okay, I'm gonna skip number 18. It's all about shapes and stuff. Basically, you have to draw them and make sure that two of the molecules have the same molecular geometry. I think the correct answer is D. All right, but you'll see it on the key. You have to draw them all out. All right, so I don't want to do that one because we're pressed for time. So I want to finish these other questions about valence bond theory because it's, I don't know, one of the more conceptual and advanced theories, because the title of chapter 9 is Molecular Geometry and Advanced Bonding Theories. Valence bond theory is absolutely an advanced bonding theory, recognizing that electrons are not dots on a page. They exist in orbitals that have to overlap in 3 dimensions in order to make a covalent bond. That is definitely an advanced theory. So look at you, learning something advanced, right? So let's look at this molecule and continue on valence bond theory. What is the hybridizations of the carbons left to right? Remember our trick, okay? What do we want to look at? What do we want to look at around this carbon atom? The number of electron domains. So how many electron domains are about that first carbon? 3. So the hybridization of that first carbon is sp2. What about that middle carbon? sp. So notice that we only combined 2 atomic orbitals, and the reason is because there are two electron domains. And then the last carbon, sp2, right? So yeah, it's sp2, sp, then sp2. All right, what do we think these bond angles are? So what's really useful is we already got electron domains. The first carbon has 3 electron domains, second carbon has 2 electron domains, and then that last carbon has 3 electron domains, right? So based upon domains, we should be able to get what that molecular structure looks like. What shape does 3 electron domains adopt in a molecule? 3 electron domains is trigonal planar, right? So if 3 electron domains is trigonal planar, what is the ideal bond angle in trigonal planar? 120, yes. But let's think about this. Do you think all these bonds are exactly 120 degrees? No, because what's screwing us up? This double bond. This double bond is real big, fat, and fluffy, right? It's really big and taking up a lot of space, and it's gonna actually push those 2 bonds a little bit closer together, all right? So this first bond angle is actually gonna be slightly less than 120 degrees, right? Okay, what about the next bond angle? All right, if you have 2 electron domains, what is that shape? Linear. So what do we think the bond angle is for 2? 180, very good, 180. But will these double bonds screw us up? This double bond screwed us up before, but these 2 double bonds, notice that they're equally big, fat, and fluffy, so they kind of cancel each other out. So it is gonna be exactly 180 degrees, this one. All right, because you have 2 double bonds on both sides. All right, and then the last one, all right, what is the ideal bond angle for this sp2 3 electron domains? Ideal is 120, but do we think it's gonna be exactly 120? Nope, it's gonna be what? Yes, greater than 120, and the reason, but you might be saying, but this last one, it was less than. But notice where the bond angle is being denoted. All right, it's the double bond that's big, fat, and fluffy. So it pushes the hydrogens closer together, but am I asking you what this bond angle is? No, you'd be right that this bond angle gets smaller, but this bond angle gets larger. So this answer, this third bond angle is slightly greater than 120 degrees, right? Okay, there we go. So if we actually wanted to order them, yeah, that's the tricky thing. So then the order would be bond 1 is the smallest, then it's bond 2, then it's bond 3, right? But the tricky one is bond 1 and 2, because one's slightly less than 120 and one slightly greater than 120, because it's where it's placed around a double bond. Okay, so then let's count how many sigma bonds are present in this molecule. So what you need to know here for valence bond theory and sigma and pi bonds is that all single bonds only have a sigma component. A double bond has two components. It has a sigma component and a pi component. And then a triple bond has a sigma component, a pi component, and a pi component. So I'm just going to go ahead, use that information and draw on this structure, all right? So I'm going to get the sigma components first. I'm going to highlight those. So every single bond is a sigma interaction, right? So there's 4 that I've highlighted already. But then in these double bonds, the first component is sigma. So how many sigma components are there total? 6. But I didn't count everything. These 2 second components of the double bond, those are our pi components. So there's 2 of them, right? So that's what you need to know, right? If there was a triple bond present, it would contribute to 2 pi components, all right? And then finally, how many total unhybridized p orbitals are required to form this molecule? Well, if there's 2 pi components present, a pi interaction requires 2 adjacent p orbitals. So this is equal to 1 pi component. So if 1 pi component requires 2 unhybridized p orbitals, then that means 2 pi components requires 4 p orbitals, all right, in order to make it. Okay, so let's keep going. Dang, okay. This is a good question. All right, so still valence bond theory. Figure out which atom adopts this hybridized orbital set. So I'm trying to show you the valence bond theory for one of the atoms, and you need to figure out which atom is it. Is it this carbon atom? Is it this carbon atom? Is it this oxygen or this oxygen? So I'm gonna give you a hint here. I'm gonna put in the lone pair so we're not confused later here. So this is the valence bond theory for an atom. We can actually just ignore this 1s set because that's an inner core electron. What we really care about is the valence shell, right? So what are we looking at here? We're looking at an atom that has what hybridization? sp2. Great. So that we can actually eliminate many of the options in this molecule, right? Because it's this first carbon, what's its hybridization? Carbon 1. sp3, so is that gonna look like this? No, it's not. So it's not gonna be this carbon because that carbon is sp3, right? So what about this oxygen? This oxygen is also sp3, so it's not gonna be that oxygen. So our 2 options are gonna be the second carbon atom and the 4th oxygen atom. Notice how the carbon has 3 electron domains, this oxygen has 3 electron domains. Both of these are sp2 hybridized, right? So now we need to decide, is it 2 or 4? So we've eliminated 1 and 3. We need to decide, is it 2 or 4? So what other information can we gather from this valence shell? How many valence electrons are on this atom? 4. So which one is it? Which element is it? Is it going to be the oxygen or the carbon? It's going to be the carbon. So our answer is element number 2, right? Because there are 4 valence electrons, right? We can also look at it this way as well. We have 3 unpaired electrons in the hybrid set. So we can also say, oh, this atom makes 3 sigma bonds. We have 1 unpaired electron in that unhybridized p orbital. So this atom makes a pi interaction. So let's look at this carbon atom. I have a lot going on, so I'm just gonna delete everything here. So we already deduced that the carbon atom right there is the element that's being represented here. I ask you, how many, what are the interactions bonding to that carbon atom? We have these 2 single bonds. Both of those single bonds are what kind of interaction, sigma or pi? Sigma. And then what is the first component of this double bond? Sigma. So that carbon atom has how many sigma bonds? 3. What does the valence bond theory say? that there's 3 sigma bonds. And then what about this component right here? What is that? That's your pi component. Is that represented in the valence bond theory picture? Yes, it is, right? So that all fits together. Okay. Okay, let's look at this. Okay, we have 2 atoms overlapping in space. That overlap is happening right here. What kind of bonding interaction is this? So it's a head-on kind of overlap. We call that a sigma interaction, all right? Pi interactions are between side-by-side p orbitals where the overlap is just not as strong, right? All right, what are the hybridizations of both of those A atoms? What do we think? Just look at how many electrons domains are around each A atom. 3, so it's sp2, perfect, all right. Could the molecule ethane, so I'll just draw it here real quick, adopt this picture? No, why? Look at that carbon. What's the hybridization of that carbon atom? sp3, so no. Ethane could not adopt this picture, right? Because the hybridization isn't correct. We would need like 2 carbon atoms that are sp2 hybridized, something like ethene. So we'd need a double bond present. All right, okay, all right, last one. Okay. Oh, this is going to be fun. How many total sigma and pi bonds are present in this molecule? So what do we need to know? All sigma bonds have what component? Just sigma. Double bonds have a sigma and pi. Triple bonds have sigma, pi, and pi. So let's go through this. Let's do the sigmas first. Let's do that in red. So all the single bonds, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Did I get all of them? No, what did I forget? The double bond and the triple bond. So how many did I draw? 13, okay, I trust you. And then all the bonds I didn't touch, those are pi components. So there's 1 right there on oxygen and then 2 between carbon and nitrogen. So there are 3 pi interactions. All right, I trust you, I'm not looking at my key. All right, what's the hybridization of the carbon and nitrogen that interact to make the triple bond, the CN triple bond? So what's our strategy? We look at those atoms, we count number of electron domains, that's how we get hybridization. So that nitrogen has how many domains? 2, so it is what hybridization? sp, and then the carbon, also sp, both of them have 2 electron domains. So they're both sp hybridized. Okay, what's the hybridization of the C and the O that make up the double bond? Okay, what's that carbon? sp2, perfect. And then this oxygen is sp also 2, perfect. All right, what's next? How many atoms are sp3 hybridized on this entire molecule? So we're looking for sp3 hybrids. So this is kind of backwards thinking, right? If it's sp3 hybridized, then how many electron domains are we looking for? 4. So you want to look, I'm just going to delete all this. What atoms have 4 electron domains? So none of the ones we just did, but this carbon has 4 electron domains, this one, and this one. So I think it's those 3 carbon atoms, right? So we'll end there. Best of luck. We have 10, okay, so we have 10 minutes. This one? Fine. Okay, if you're gonna leave, then just leave so we can finish this question. Or not, I don't care. You can leave if you want, but I was asked to do this last question. I just didn't want to do it because I have to draw 8 molecules. All right, so here's the thing. I'm not going to do the 6 steps of the Lewis structures. I'm gonna just draw them and we're gonna inspect them using VSEPR theory. So let's look at the molecules here. I hope at this point we've done BF3 a lot now. So that's what BF3 looks like. NH3 looks like this, where nitrogen has a lone pair. So notice both molecules have 3 bonds to it, but one of them has a lone pair. So that lone pair really screws up the structure of NH3. So our strategy here to find molecular geometry is we first need to figure out electron domain geometry, where we count, okay, that boron has 3 electron domains around it. That makes it trigonal planar. But because there's 0 lone pairs, that means its molecular geometry is also trigonal planar, right? That every single electron domain is a bond, so they're literally the same, all right? There's no lone pairs we have to count for. But when we look at NH4, how many electron domains are there? 4, all right? What do we call something with 4 electron domains? What shape is that? Tetrahedral, very good. All right, so that's tetrahedral. Those 4 electron domains, are all of them bonds? No, one of them's a lone pair. So I always tell my students this, you can't see lone pairs, you can't see them. So to figure out the molecular geometry, start with the electron geometry, and you cover up the parts you can't see, so cover up the lone pair. So how many things do I cover up on this molecule? Just 1, right? So I'm gonna cover it up. And then you have to tell me what shape is left over. It looks like a triangle, right? But is it flat? Nope, it is like a pyramid. So what's left over is trigonal pyramid. I can draw it in, on paper as well. So here you start with a tetrahedron. There's 1 lone pair present right there. So the analogous thing, since you won't have a model on the exam, you can draw this and literally just erase that lone pair and tell me what shape is left over, right? So it's trigonal pyramid. If you're gonna get this one wrong, you're gonna think NH3 is trigonal planar. If you do that, then you forgot about the lone pair, you just ignored it. So the idea here is your molecular geometry has to template on your electron geometry. When you consider lone pairs, you just cover up parts of your electron geometry you can't see. So let's do the next one, CO2 and OF2. So I'm just gonna draw those. So there's CO2, and then OF2 looks like this, right? So I guess the answer to this first one, no, they do not have the same shape. One of them is trigonal pyramid, the other one's trigonal planar, right? So they're not both the same geometry. This next one, at first glance, you might be like, yeah, both of these things are linear, but that's not true. Let's look at CO2. I didn't draw the lone pairs because I didn't feel like it, but CO2, how many electron domains? 2. What do we call that shape? Linear. Is everything a bond? Yes, so that means our molecular geometry is also linear, since there's 0 lone pairs, okay? But is it the same thing for the second one? No, because how many electron domains are there? 4. Did we say 4? 4, okay, all right. And so what is 4 electron domains? Tetrahedral, but is every single thing a bond? No, and we can't see lone pairs. So what we're gonna do, I can just draw it, right? Here is your electron geometry template. 2 of those things are lone pairs. So I'm just gonna draw those in. And then do what? Just erase them. You erase them and you just state what shape is left over. It is bent. Yes, so this is a bent shape. What do you think the bond angle is here, approximately? Is it gonna be 120? No, so let's just back it up a little bit. What was the original shape? Tetrahedral. Remember, what is the shape of a tetrahedral? What's those bond angles? 109.5. So when I erase those lone pairs, the leftover bond angle is going to be really close to 109.5. But remember, lone pairs, like double bonds, they're big, fat, and fluffy. And what do they tend to do? Push bonds a little closer together. So it's actually going to be slightly less than 109.5. Yeah. Yeah, so I don't have, so the question was, do we only care about the central atom? The answer is yes. Okay, when we're trying to figure out shape, what we care about, notice here, We only care about that central atom. That's what's dictating our shape. These white balls, they could be hydrogen atoms, but in this case, they're fluorine atoms. Those fluorines do have lone pairs, but I don't care about the electron domains around those guys. All right, does that help? Okay. So do these shapes match? No, they don't. One's bent. This one's bent. Okay. 3 minutes to do 2 more. Okay, CF4, SEF4. So CF4, SEF4. Right? So at first glance, you might be like, oh yeah, those are the same shape. Both of them have 4 things attached to them. But what's probably going to screw us up? Lone pairs, yes, they always do. So CF3 looks like this. All right. The fluorines have lone pairs. I just don't feel like drawing them. SEF4 looks like this, where if you do count the electrons and do all of that stuff, you'll see that the selenium has 1 lone pair in the middle. Actually, I think we drew this molecule earlier. All right, it looks like this. So just right off the bat, are they going to have the same shape? No, they're not, but let's actually get their shapes. All right, CF4, 4 electron domains, 0 lone pairs. What is its molecular geometry? Tetrahedral, because there's no lone pairs to consider. You don't have to cover anything up. All right, so the next one, the selenium one, has 5 electron domains. What do we call that? This one's the trigonal bipyramid, right? So I'm going to go ahead and draw that. So trigonal bipyramid looks like this. You have like an axial 2 bonds that are 180 degrees from one another. And then you have 3 bonds that make up what I call the equatorial position. It's like the belt region. That belt region has 3 bonds that are all 120 degrees away from one another. It's like you have a square plane, or you have a trigonal planar and a linear thing kind of together in the same molecule. So that is the electron geometry, but just like the other things, is every single domain a bond? No, one of them is a lone pair, right? But trigonal bipyramid is tricky because there's 2 different environments. We have a choice. We could put a lone pair here, or we could put a lone pair like here, right? So what we'll see here is that lone pairs, they're big, fat, and fluffy, so they're going to prefer to be where there's more space. There's more space in the equatorial position, so that lone pair is going to go right here. It's not going to go here. It's not going to go there because there's less space. The closest bond is 90 degrees away from that position, but if you put the lone pair here, then the closest bonds are 90 and 120 degrees away from it. So this spot is just more spacious. So just like before, place the lone pair, then erase it and tell me what shape is left over. What do we call that? That is a seesaw, all right? So here the shape is seesaw. So obviously these 2 do not match their shapes either, okay? But what we're learning here is the process of VSEPR theory. That's the important thing here. And so clearly the last one is the correct answer. So those 2 molecules, oh my gosh, I need another page. All right, the last molecule is CH2O, and what's the other one? Carbonate. All right. So these molecules look like this. This is what this molecule looks like. And then carbonate looks like this. Right? Carbonate does undergo resonance. All right, so with those 2 molecules, what are we doing? We're looking at that central atom, counting the electron domains, and hopefully this makes us very happy because both of them have 3 electron domains. Both of them have 0 lone pairs, so both of them adopt what shape? Trigonal planar, yes. Even though I drew these molecules like they technically look T-shaped, I'll point out that the way that we draw Lewis structures don't necessarily show what they look like in 3 dimensions, all right? All right, so best of luck, everybody, in your studying. Have a great evening.